All right, good morning, chemists. We'll get started here. We're going to jump right into it. Last week, we talked about or introduced two new ideas, or our last two equations in this chapter were Heisenberg's uncertainty principle and the de Broglie wavelength equation, where we have this new way to describe electrons. So previously in the chapter, we talked about light behaving like both a wave and a particle, so we extended that idea to electrons as well. So this is what gives rise and allows us to solve the Schrodinger equation for orbital shapes. So you might have learned about orbital shapes, the S, the spherical one, P, the dumbbell shape, and then D orbitals, the butterfly shape. So these shapes come from us treating electrons like waves, although they are particles. So we talked about the de Broglie wavelength equation, where all mass in motion has a wavelength that we can calculate. And for electrons, particularly because they're small, they have fairly large wavelengths that become significant on the atomic scale. Then we introduced the idea of Heisenberg's uncertainty principle, where we can't know a particle's position and its velocity to certainty. There has to be a minimum amount of uncertainty there. And this, again, becomes important when things are really, really small, like electrons. So we calculated the minimum amount of uncertainty in an electron with some uncertainty in its velocity here. We plugged the uncertainty values into Heisenberg's uncertainty principle. So note here how velocity is given in this question. It says, okay, the velocity is about 6 plus or minus 0.05 times 10 to the 6th. We only really care about this uncertainty part attached to it, not the actual velocity. That's the number that goes into the uncertainty principle. And then we can calculate the uncertainty of this electron is some minimum. The minimum amount of uncertainty here is about 1 nanometer. And so with this uncertainty, this is where we get orbital shapes. And that's coming up here too. And I promised you that, the point of this chapter, hopefully, is to make you more aware of some of the comic strips and memes out there. And one of those is Schrodinger's cat. Anyone, you see things about Schrodinger's cat online and hear about it? Yeah, it actually has to do with the idea that electrons are hard to locate until you take a measurement. And that's the whole idea of Schrodinger's cat, that you have a cat. So Schrodinger came up with this thought experiment that you have a cat in a box with poison in it, some type of poison. And so when the box is closed, it's kind of like an atom. When the box is closed and you know that there's a cat in there with poison, you don't know for certain if the cat has ingested the poison or not. So the cat, before you open the box, is both dead and alive at the same time, because you don't know for certain until you open the box. But once you open the box, then you what is called collapse the wave function, and you take that measurement, and now you do know for certain whether the cat is dead or alive. So that's the whole point of Schrodinger's cat. It's just like a thought experiment that relates to the uncertainty that is associated with an electron. And so the idea that the cat is both dead and alive, or an electron is kind of hard to locate, this is the whole idea of quantum superposition. And so that term kind of relates to I watched Ant-Man and the Wasp a couple weeks ago, and the main antagonist in that movie is that girl who is all shifty. Do you know what I mean? The shifty girl. And yeah, so that shifty girl, the idea that her atoms are kind of in two places at once is kind of the embodiment of quantum superposition, that you're in two places at once. You have a lot of uncertainty there. So hopefully you understand quantum superposition, or Schrodinger's cat, and how that relates to Heisenberg's uncertainty principle and the idea that electrons can be hard to locate. All right, so what does this have to do with orbital shapes? Well, because we can't locate electrons in space, that they have to have some large amount of uncertainty in their position. So instead of saying, hey, you have an electron right here, orbiting at some finite distance around the nucleus, instead we're going to say, oh, we have electrons, we have a probability of finding electrons in this space. That's how we get around Heisenberg's uncertainty principle, so we don't violate it, by saying you're going to find an electron in this space. That's how we introduce a large uncertainty in position there. And so these shapes are using this fact that we have this large uncertainty in position. So we're combining the ideas of Heisenberg's uncertainty principle and solving the Schrodinger equation here. So that's where these s, p, and d orbitals come from. And then finally, the end of this chapter, we'll finally start filling electrons in these orbitals once we learn what they mean. All right, so how did they figure out this, the orbital shapes like S, P, and D? Well, Erwin Schrödinger, together with the ideas from Heisenberg and de Broglie, basically he used the idea that electrons are waves and formed a new type of math, so quantum mechanics, treated electrons as a wave and made a wave function to describe an electron. And so once you solve the Schrödinger equation, which is the wave function of an electron, this is where our different quantum numbers come out of when you solve that equation. So quantum mechanics is just a new type of math to describe energy. So this equation does look kind of complex. There's like pitchforks, there's upside down triangles, and so if you take higher level math, you will interact with things like this. But I just want to show you that this equation, we are just treating our electron like a wave. And this equation actually isn't too different from what we've learned before. Do you remember in Chapter 5, we talked about internal energy? Internal energy of a system is equal to all of the kinetic energy and all of the potential energy in your system. So if we actually look at this wave function equation, it might look similar to you. So here, this term is talking about the mass of the particle. That to me kind of sounds like kinetic energy, where we're taking into account mass, its velocity, right? If we look at this term, it says it describes the forces that are acting on the particle. So that to me kind of sounds like potential energy, while this first term kind of sounds like kinetic energy. And so if we add those two things up, we get the total energy of our system. So basically, using this new type of mathematics is very akin to classical mechanics, but it just uses fancier math, all right? And so once obviously we are not going to solve this Schrödinger equation, but what does come out of it once you solve it are our quantum numbers that we will talk about. So we're going to be just talking about the solutions to the Schrödinger equation, but I just want you to be aware of where those numbers come from. They come from the solution in this equation. So if you're ever like at a bar or something and you see this equation, in the background of like a TV show or something, you can impress your friends and be like, oh yeah, those are upside down triangles, so it's probably the Schrödinger equation in the background of like whatever TV show you're watching. All right, so the Schrödinger equation 100% correctly predicts the energy levels of our hydrogen atom, and it predicts the observations of the line spectrum that we observed earlier in this chapter for our hydrogen atom. So, but basically all the Schrödinger equation does is it introduces the idea of these orbital shapes, that we have this strange, poorly defined space where you will find an electron. So yeah, adding this idea of uncertainty now gives us experimental observations here that match what we actually see in a line spectrum exactly. And so if we compare the ideas of like the Bohr model, which we just came from, now we add the idea of uncertainty with the Schrödinger model. The Schrödinger model does predict everything exactly because we add the idea of uncertainty. In the Bohr model does violate the uncertainty principle because we said earlier that we have the electron orbiting our nucleus. nucleus, and in that case, we would have a very well-defined certainty of finding the electron. So in that case, for the Bohr model, does violate the uncertainty principle. So that's just comparing the two ideas, but the Bohr model will still get you like 95% of the way to the idea of our hydrogen atom, but the Schrodinger equation, it 100%, once you solve it, describes our hydrogen atom. All right, so there's that. And just for completeness, so I showed you the Schrodinger equation, so this equation is the actual solution to the Schrodinger equation. Yeah, it looks real complex. No, you do not have to memorize this. What I wanted to show the solution to the Schrodinger equation because this is where we get our quantum numbers from. So you see terms like our n values, our L values, our ML values. So those values we're going to talk about and relate to our periodic table here very soon. So we see here with the Schrodinger model, we have these different orbital shapes. This relates to this large uncertainty in our position. And so we're going to use these quantum numbers to describe the probability of finding the electron. So the different quantum numbers that we're going to talk about here are N, L, M sub L, and M sub S. These are our solutions to the Schrodinger equation, which is this equation. Right? So obviously do not memorize the equation. What we want to memorize here are the significances of the solutions to the Schrodinger equation, the actual quantum numbers themselves, but I wanted to show you the mathematics behind it. So if you do take a higher level chemistry, it's kind of a rite of passage in physical chemistry, which is kind of like Gen Chem 3, sort of, where you do solve the Schrodinger equation. You solve it once, and then you never solve it again because now we just have computers to solve the Schrodinger equation for us. All right, so let's look at our quantum numbers. So maybe you'll go through that rite of passage here soon. Okay, these are our quantum numbers. These are how we are going to find our electron, how we tell the reader the probability of finding an electron in this space. So these different quantum numbers, N, L, M sub L, we'll go through each one, are associated with different factors of finding our electron. Our first quantum number here, N, is the size. So how far away are you going to find your quantum or your electron around your nucleus? Right? Also, that N quantum number also describes the energy of the electron. Right? So size and energy, those are related. The next quantum number, L, this is our angular quantum number. This tells us the shape, what shape will find our electron. And then the last one here, M sub L, tells us the orientation of that particular shape. All right, so we'll go through each one. So the first one is our N quantum number. This is our principal quantum number. This identifies what shell or how far away your electron is from the nucleus. And so all of these N quantum numbers are integer values. Actually, most of these quantum numbers are integer values. So our N quantum numbers can be like 1, 2, 3, so any integer other than 0. And so what we see as N increases, typically the size of our orbital increases and the energy of our orbital increases. So I have over here kind of some examples. Okay, I'll make it so you can see that. Some examples. Here is an electron in a N equals 1 energy level. All right, it's specifically an s orbital. We'll talk about that later, but we see that the shape here is smaller, that finding an electron in an n equals 1 orbital, you're going to be overall closer to the nucleus versus if you compare that to an n equals 2 electron. So that would be like this electron up here, or this electron down here would be 1s. So we see this n equals 2 electron is both higher in energy and overall further from our nucleus. Right, so as n increases, we see the size, the probability of finding our electron gets further away from the nucleus, and energy increases. All right, so that basically just relate n to size. All right. Okay, so that's n, energy or size of our electron. So next we'll talk about shape. So in this example, I'm showing s orbitals. All right, so that shape is directly related to our secondary quantum number or our angular quantum number L. So this number tells us the number of angular nodes in our orbital shape. And so there's a little bit of memorization that has to come from here. So for L quantum numbers, there's different possible numbers. They start at 0 and they go, they have integer values, so like 0, 1, 2, 3, 4. So each of those values has a certain shape associated with it. So, So here, an L quantum number of 0, this 0, this is the number of angular nodes in the shape. And I have an analogy to help you with these shapes. So an L of 0, we say, has an s orbital shape. And so an s orbital looks like this sphere, all right? S orbitals, this is an L equals 0, all right? It looks like a sphere. Next up, if we increase our L quantum number to 1, so L equals 1, this is what we call a p orbital, and we see it looks like a dumbbell, all right? And then next, the next one, L of 2, would be our d orbitals, and we see that this looks like a butterfly. You see that? All right, so I mentioned that these numbers represent the number of angular nodes in that specific shape. So angular node is like not a word that we typically associate or can distinctly see these shapes. The analogy I like to use with angular nodes is the L quantum number. So think of orbitals like a balloon animal, all right? And the L quantum number is how many times you twist your balloon animal. All right, so if you start with a balloon and you twist it 0 times, it's still a circle, right? Yeah. Okay, then with L equals 1, we twist the balloon once. So if you think about it, you take that balloon, you twist it once, what is it going to look like? A dumbbell. So in that case, we've increased the number of lobes on the shape to 2, but we only twisted it once. So that's where that L equals 1 comes from to give us our p orbital shape. And then finally, our d orbital shape. So we twisted our balloon once to make a p orbital, then fold the balloon in half and then twist it again. All right, so then L equals 2, so now we have this kind of butterfly shape that comes out. And so we see in a d orbital with an L equals 2, we have 4 lobes that come out. So I like to think of our L quantum number, it's the number of angular nodes, it's how many times you twist your balloon animal, all right? And so we do see that we increase L can be 3 or 4, and we can get F and G orbitals, but those aren't super common, so we're not gonna go into much detail there. What we will surround ourselves with are S, P, and D orbitals. So now that you know the shapes, we need to set some rules on the possible shapes you can have based upon what n level you're in. So the possible subshells or the possible shapes you can have depend on the energy level of that electron, so the n value. So the rule is that the possible L values are the values between 0 and n minus 1. So if we have an electron that's in an n equals 4 energy level, our possible shapes that we can have will be 0, 1, 2, and 3. Those are our possible L values. So for an n equals 4 electron, we can have electrons in S shapes, P shapes, D shapes, and F shapes, but we can't go past that, all right? Okay, so depending on where, what n level and what shape your electron is in, we can say exactly what subshell that electron is in. So for example, if we had an electron that was in n equals 3 and its L equaled 1 to locate that electron, we would say that that electron is in a 3p orbital, where that 3 tells us the n level, and then the p indicates what L quantum number we have. So since I said that L equals 1, we can have a p shape there. But there will also exist 3s and 3d electrons as well, but the specific electron we are talking about is an electron in a p shape. Right, so we'll look at other examples and kind of come up with all the quantum numbers that come out depending on what n level we're in. All right, so let's do a couple examples here. So let's name all the subshells. So this means our L quantum number that can possess an n equals 5 electron. So the idea here is, okay, we're in an n equals 5, that's our energy level. So let's think of all the possible L values we can have. when n equals 5. And so the rule is up here, all right? All of our possible L's are all the numbers between 0 and n minus 1. So the possible L's will be 0, 1, 2, 3, and then 4, and that's it. All right, so all of those numbers have letters too. So if we actually want to name the subshells, this will be a 5s orbital, a 5p orbital, a 5d orbital, a 5f orbital. So that's our L equals 3, and then finally L equals 4. After F, it just goes in alphabetical order, so 5g orbital. That would be possible. All right. Okay, so those are all the possible subshells in an n equals 5. All right, and so let's look at this next problem. Why is there no such thing as a 2D subshell? All right, so let's kind of break this apart. All right, so 2 indicates what quantum number? The 2. N, yes, that's the n value. So n equals 2. All right, so if we think about it kind of backwards here, if n equals 2, what are the possible L quantum numbers we can have? 0 and 1, and that's it. So at this point, if we've identified our L quantum numbers, these actual orbital shapes would relate to a 5s orbital, or not 5s, a 2s orbital and a 2p orbital. That's it. Right? So the reason that a 2D subshell does not exist is because D is related to an L equals 2, and that's not possible for an n equals 2 electron. Because of the rule, all the possible L values are always all the integers up until n minus 1. All right. Okay, so those are some possibilities there of using our quantum number. So that is our L quantum number. This relates to, I like to think about it as shape. So S, P, D, those different shapes. So now let's talk about the last quantum number, and that is our magnetic quantum number. This determines the orientation of each of the orbitals, all right? The unique different orientations that each orbital has. And also, ML also will relate to how many electrons can fit in these different subshells. So I like to relate it to if you've filled electrons before, you might have seen boxes that look like this. All right, so these boxes are places that we can put electrons, all right? Typically, we can put 2 electrons in each box, all right? So each ML quantum number that we can have relates to one box. So these ML quantum numbers, these are our different orbitals that we can have in each orbital shape. And so an orbital, when we talk about orbitals, is a box in this picture. So the rules for magnetic quantum numbers, it depends on what subshell we're in. So it depends on what what shape we're working with. Are we working with an s orbital, a p orbital, or a d orbital? And so the rules here are the possible ML quantum numbers depends on what L quantum number you have. And so the rule is the number, the ML quantum numbers we can have are all of the integers between negative L and positive L. And so I think it's best if we just go through the different examples here. So for an L equals 0, this is an s orbital. The only possible ML value we can have is 0. So in an electron orbital diagram, there's just going to be one box for an s orbital. For an L equals 1, what kind of orbital shape is that? P. Yep, so that's a p orbital. And so if we follow our rules for MLs, it's all of the integers between negative and positive L. So we can see that the possible MLs that we can have are -1, 0, and +1. So since we have 3 different ML values, 3 different orbitals, we draw 3 different boxes for a p orbital, or sorry, for a p subshell. There are 3 boxes. Right? And you can see that here. See, there's 3 different orientations of a p orbital that we can have. So see how s orbitals have 1 orientation, 1 box. P orbitals have 3 orientations, 3 boxes. And so you can see the kind of trend here if we look onto a d orbital, which is L equals 2. The possible numerical values of the magnetic quantum number for a d orbital or d subshell is -2, -1, 0, +1, and +2. So how many numbers did I write? How many orientations are there? 5. So how many boxes are there going to be? 5. Yeah, so each of these boxes is one of these orientations. Each of these boxes can hold electrons. All right? All right. So, and this is something specific to all of our subshell shapes. All s orbitals will have one box. All p orbitals, whether it's a 1p or a 2p or a 3p, will have 3 boxes. All d orbitals will have 5 boxes, right? Because our ml quantum numbers are always related to the L quantum number. All right, and so that's what you see here in our orbital diagram. All of our s orbitals have 1 box. All of our p orbitals, whether it's 2p or 3p, have 3 boxes. All of our 3d electrons or orbitals here have 5 boxes. All right, so in general, what you'll see is that the number of boxes, the number of orbitals in a subshell are 2l + 1. All right, but you can also determine that by determining the possible values of our ml quantum numbers. All right, so let's do these problems. So how many orbitals, or in theory, how many boxes are in a 2s orbital? How many boxes? Just 1, yes, just 1. Because an s orbital, L equals 0, and so our only possible ml is 0 in this case. All right, so how many orbitals are in a 3s subshell? How many boxes? Just 1, yep, because again, it's still an s orbital, all right? All right, how many orbitals are in a 2p subshell? 3, great. And then how many orbitals are in a 3d subshell? 5, very good. So essentially, we're just looking at different sets of boxes here and just counting how many boxes are there. So those orbitals are different orientations of finding our electron. All right, so those are our 3 quantum numbers. We'll add the 4th one. That's when we actually start filling electrons. So let's do an example here. Let's get what are the possible values of all 3 quantum numbers for an n equals 3 energy level. All right, so I'm telling you, we have an electron in n equals 3. Where are the possible places we can put that electron in n equals 3? So I like to think to myself, okay, what are the possible L values we can have for n equals 3? All right, so what are the possible L values we can have? 0, 1, 2, and that's it. That's it. So for each of those L values, we have possible ML values that we can have. So we have to go through each of those L values individually. All right, so let's just do the first one, L equals 0. All right, this is an s orbital, if we want to be specific, but what are the possible ML values for an L equals 0? Just 0, because remember the rules for MLs, it's all the integers between negative and positive, the L value. All right, and then for L equals 1, our possible ML values we can have are -1, 0, +1. And then for L equals 2, our possible ML values are -2, -1, 0, +1, and then +2. All right? So those ML values that we just got, those are the possible boxes that we can have to put electrons. So in L equals 0, we have 1 box. In L equals 1, we have 3 boxes. And then in L equals 2, we have 5 boxes here. All right, so if we count how many boxes there are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 total orbitals that we can have. All right, there's 9 orbitals that we can have. Okay, all right, so then the last idea here, these orbitals, these boxes are places we can place electrons. So how many electrons can possess an n equals 3 quantum number? So I actually didn't introduce the idea of placing electrons yet, but if I tell you that we can put 2 electrons in an orbital, or essentially, 2 electrons can go in a box. How many electrons can fit in those boxes that we just found? 18, yeah, so 9 boxes times 2 electrons each. There are 18 electrons that can fit in those orbitals with an n equals 3. All right? Okay. So yes, and then so here are just kind of some tricks to get to the right answer numerically, but you can always do it also kind of manually looking through all the possible quantum numbers here. For any n level, so in this case n equals 3, the number of possible orbitals, the number of possible boxes, if you go through all of these steps of determining all the L's, determining all the m sub L's, is always n squared. And then to get the number of electrons that can fit, as long as you know 2 electrons in a box, just multiply the previous number by 2 to get how many electrons can fit in that n level. All right, so those are our 3 quantum numbers. So let's go to the 4th one, and I should have introduced this one first actually, and that's our ms, or our spin quantum number. This idea of electron spin allows us to put 2 electrons in a box. So each of these orbitals is a box. Each box can fit 2 electrons, but we can only fit 2 electrons in a box if they are opposite spin. All right, so we can't, so I'll just draw a bigger box here. All right, so there's my orbital. We cannot put 2 electrons in a box where they're spinning in the same direction, and it's because of Pauli's exclusion principle. So we can't have this, both of them are spinning the same direction. Instead, we have one spinning up, one spinning down, and so numerically, this ms quantum number would be something like +1/2 and -1/2. So that allows us to put 2 electrons in each box, where we introduce the idea of spin. All right? So that is our 4th quantum number. It allows us to put 2 electrons in each box as long as both of them are spinning in opposite directions. So we have +1/2 and -1/2. Those are our only possible spins that we can have for a single electron. Okay. All right, so let's do some examples, some more examples before we move on with quantum numbers. All right, so here are 5 different examples of 4 quantum numbers, and you tell me, is this a valid set of quantum numbers for an electron? Is it possible to have an electron possess these 4 quantum numbers? So the strategy here is to remember what are the types of values we can have for the different quantum numbers, and think about, do these numbers relate to or not defy any of the rules set out for our quantum numbers that we already talked about. So if we just go through all of them one by one, we can see, okay, do any of these numbers violate the rules that we set? All right, so the first one. I like to think, okay, if we have an electron in an n equals 3, what are the possible L values we can have? 0, 1, and 2, right? So is that L value okay? Yes, it is okay, because we can have a L equals 1. Yes, okay. Then once we've set our L value, all right, so L equals 1, what are the possible ML values we can have for an L equals 1? -1, 0, +1. So is the ML okay? Yes, it is. Perfect. Okay. Yes, that's good. What about that spin, a +1/2? Is that okay? Yes, yep, that's okay. All right, so it looks like A is okay. Can you tell me what orbital, what kind of subshell this electron is in? It's in an energy level of 3, so it's a 3 what electron? So L equals 1 here, so that relates to what kind of orbital? P, yes, P. So L of 0 is S, L of 1 is P, L of 2 is D, but specifically this electron is in an L equals 1, so it is in a 2p orbital. So if we drew out the boxes, it's an electron in one of those 3 boxes. Yeah? Because it's 1/2. The only allowed spins that we can have are +1/2 and -1/2. That's it. Okay, yes. Okay, so next one. All right, so this is so that one's okay. A is okay. It's in a 3p orbital. So the next one, n equals 3. So same idea. The possible L's we can have for an n equals 3 electron are 0, 1, and 2. So is the L value okay? Yes. Is the ML value okay for that L? No. What should it be? It has to be 0. So this one is incorrect. We cannot have an ML of -1, all right, in an s orbital, because that's what this is trying to say. An n of 3 and an L of 0, this is describing a 3s orbital, and a 3s orbital only has one type of box with an ML of 0. All right, so we can't have a -1. So B is incorrect. All right, let's keep going. C. All right, if n equals 2, our possible L's are 0 and 1. So it looks like that L is okay. So what kind of orbital is being described here? A 2p, 2p, great. So how many boxes in a 2p? 3, yes, 3 boxes, great. All right, is that ML okay? Can a p subshell have a ML of 0? Yes, it can. Okay, perfect. Yes, because one of these, if we kind of label these are the different orientations. It's going to be -1, 0, and +1. All right, so yeah, 0 is one of those boxes. All right, can we have a spin of 0? No, so that's the incorrect one. How can we make this correct? Just change the spin to either +1/2 or -1/2. Because once we do that, then we could have like an electron like this, and it would be A-okay. All right, but we can't have a spin of 0. All right. All right, next one, D, n equals 3. So our possible L's again are 0, 1, and 2. So this is the L okay? Yeah, what subshell is this? 3D, yes. Can a 3D subshell have an ML of 0? Yes, it can. Can it have a spin of -1 or -1/2? Yes, it can. So let's draw it. A 3D subshell has how many boxes? 5. So 1, 2, 3, 4, 5. Each of those boxes are its possible ML values. So we have -2, -1, 0, +1, +2. So we're just going to put an electron in ML equals 0 with its spin down. So it's going to look like that. And that's okay. We can do that. Okay. All right, the last one. E, n equals 1. So that means our possible L values are only 0. So it looks like this combination of n and L are okay. So what subshell is being described here? 1s, yes, 1s, because we want to say what energy level it is. All right, can we have an ML of -1? No, we can't, because 1s is just one box, and the only possible ML is 0. That's it. So that means that ML does not work here. So E is incorrect, C was incorrect, but D and A were okay. All right. So those definitely harder to recognize, okay, what combinations are incorrect versus correct. All right. So those are the possible quantum numbers we can have. So we've talked a lot about these integer values, all right, so our N, L, ML quantum numbers. Let's talk about what they actually mean, all right? So we talked about the numbers, but their meanings actually give rise to, or those values give rise to the actual shapes that we see. So we're going to talk about these different orbital shapes, relate them to those integer quantum numbers, and think about them graphically of where will we find electron density based upon those quantum numbers. And we can kind of represent where to find electrons 2 different ways. Either we can use electron density models like you've seen here, like you see the sphere, the dumbbell, the butterfly, or we can use radial probability functions, these graphs, to kind of also tell us similarly where we will find electrons, but using polar coordinates instead. All right, so remember, all of these quantum numbers come from us solving the Schrodinger equation. But will I ever ask you to solve the Schrodinger equation on the exam? No. But what will I ask you to do? Just use quantum numbers, all right? But I will never ask you to solve this. All we do is just ask you about these specific quantum numbers. All right, so our different quantum numbers, we have N, L, M sub L, right? So that L quantum number tells us the shape of our orbital, and I mentioned this before. That L value tells us the number of angular nodes, or sometimes it's called nodal planes, in that orbital shape. So for example, L equals 0, there's 0 angular nodes, so how many times do we twist our balloon animal? 0 times, so that's why it's a perfect sphere. But L equals 1, this has one angular node. So remember, all of these L's, these are angular nodes, Right, L equals 1, we have one angular node, we twist the balloon animal once. L equals 2, we twist the balloon animal twice, but we have to like fold it in half first and then twist it to get that butterfly shape. And then L equals 3, this is our F orbital. We twist it 3 times and we get a lot of different nodes that come out of that shape. All right, so again, what I want you to see here are these L values give us the shape, but the number of different orientations here. So see how these different p orbitals, this p orbital is along the x-axis, this one's along the z, this one's along the y. Those are our different ML combinations. That's why we have three different orientations, 3 different boxes here. All right, so L's give us our shape. It's related to angular nodes, so do remember that. Okay, so let's go into detail of where we find electrons on our different types of s orbitals. So an s orbital has what kind of L value? 0. So how many angular nodes does an s orbital have? 0. It's just a perfect sphere. All right, so again, a couple ways that we can talk about s orbitals. We can just draw them in a contour model, like in a 3-dimensional space. But so where these numbers actually come from are from solving the Schrodinger equation. So if we solve the Schrodinger equation for a 1s electron, we'll see this probability function of finding an electron in this space when we get away from the nucleus. So we see this is an example of a 1s electron where I'm trying to tell you, oh, you're going to be finding most of your electron density right here, all right, away from your nucleus, right? If we upgrade to a 2s orbital, right, we see that the radial probability function changes a little bit. So the solution to the Schrodinger equation is a little bit different, but because the quantum numbers are different. In a 2s orbital, n equals 2, L equals 1. But in a 1s orbital, n equals 1, L equals, oh no, it doesn't equal 1. Sorry, it equals 0. There we go, 0. All right, and then in a 3s orbital, n equals 3, L equals 0. So in all of these, L equals 0, but the n numbers change a little bit here, right? And so what we see is the graphs change a little bit. The probability of finding an electron in a 2s orbital looks a little bit different from our 1s orbital. And so this is what you see here for a 2s electron. Most of your probability of finding an electron is going to be further away from your nucleus, but there's still a tiny probability you might find an electron kind of close here, right? But we see there's a couple of spaces where the graph goes to 0. And so right there where that graph goes to 0 is what we call a radial node. So a 2s electron, if we look at the radial probability graph, has one radial node where there's a spot where the graph goes to 0, that you will never, you'll have a 0% probability of finding an electron between n equals 1 and n equals 2. That's basically what that means. The idea that we can only have electrons in integer value energy levels, right? So most of your probability will be finding an electron either here or up here a little bit further away from our nucleus. And so we see for a 3s orbital, it kind of looks similar, but now we increase our number of radial nodes, that the number of times this graph goes to 0 is actually twice, all right, twice. Where I like to think, okay, this bump is kind of our 3s shell, this bump is our 2s shell, and then this bump is our 1s shell, essentially, right? So that the number of bumps here is kind of telling you, oh, you can have an electron of this energy. Most of the time it's going to be in this 3s subshell, but it might be in kind of those inner layers, 2s or 1s, a very small amount of the time, right? So this graph has 2 radial nodes. So I have the definition of a radial node. It's where the number of times your graph goes to 0, but don't count the ends of the graph, right? Because we see here, you're not going to find an electron infinitely away from your atom. And you're also not going to find an electron at a radius of 0 because that's inside your nucleus. You're never going to find electrons inside your nucleus. So those ends of the graph don't count as zeros. It's only the inside. So let's finish these number of radial nodes. How many radial nodes does a 1s orbital have? 0, yeah, because the inside of the graph never goes to 0, right? So the number of radial nodes we can get from the graph, but we can also calculate it by an equation, right? So the number of radial nodes for any type of orbital will always be the n value minus the L value minus 1. And so we are already calculated these n and L values, so you can actually calculate from these values the number of radial nodes that have to come on a 1s orbital is equal to 0, because it's 1 minus 0 minus 1 equals 0. Same thing for a 2s orbital. So it's 2 minus 0 minus 1. So there's going to be 1 radial node. For a 3s orbital, n equals 3. So it's 3 minus 0 minus 1 gives us 2. So we can also use this equation to predict how many radial nodes are in our radial distribution function graph. All right. Okay. So let's look at another one. Let's look at a p orbital. Let's remind ourselves how many angular nodes are in a p orbital. How many times do you have to twist the balloon animal? Once, yes. Okay, because that's what L is. L equals 1, we have a p orbital. Okay, so we see here our contour maps are a little bit different. So we can find electron density kind of on two sides of our axes here. Right? It doesn't mean that electrons are kind of like moving in a figure 8 configuration in a p orbital. It just means that there's equal probability of finding an electron either above or below the plane here. Right? That's really all that means. Okay, so let's apply our idea of angular and radial nodes again. So let's, okay, so how many angular nodes are on a p orbital? Angular. 1, yeah, we already got that. Angular means L. Okay, so I give you this graph. If I tell you that this graph is showing you a radial distribution function of a p orbital, tell me what kind of p orbital it is. Well, let's first, how many radial nodes are present in this graph? 0, yeah. It's basically I'm asking you how many times does the graph go to 0? Don't count the beginning and end, and so there's none. All right, so tell me what orbital, what kind of p orbital is being depicted here? A 1p, a 2p, or a 3p? It is a 2p, yeah. So remember, the number of radial nodes present in a graph is n minus L minus 1. So we can just kind of figure out what's the missing piece here. This graph has 0 radial nodes. I need to figure out what the n value is. I tell you it's a p orbital, so that tells you what L it is. L is 1 minus 1. So what's the missing piece? N equals 2 in this equation. Yes, n equals 2. So if n equals 2 and L equals 1, because I told you it's a p orbital, this is a 2p orbital. All right. Okay, so that's kind of a backwards way to ask a similar question, different from the ones that I asked in the previous one. All right. Okay, so I've been throwing around the terms nodes a lot. We got angular nodes, that's related to L. Radial nodes is related to our radial distribution function. Probability of finding an electron based upon its distance from the nucleus. All right, so here are our different orientations for d orbitals. Right, most of them look like butterflies except one of them. All right. Okay. So how we designate d orbitals, we have like d, y, z, d, x, z, d, y, x, y. So those x, x, y, z designations tells us how our butterflies are oriented on an x, y, z coordinate system. All right. So just so we can be more specific here, dz squared, you can see it kind of looks like a p orbital, but with a belt around it along the z-axis. So do make sure you know the difference between a dz squared orbital and a pz orbital. It will look similar. A pz orbital will look similar where it looks like a dumbbell. It just doesn't have a belt on it. All right, so do know there's a difference between those. All right, so for d orbitals, how many angular nodes are on a d orbital? 2, yes, because that's the L value. All right. And so remember the possible MLs, there's 5 different orientations. That's why there's 5 pictures here. All right. Okay. All right, so let's do these questions. How many angular nodes does a 4D orbital possess? Angular node. So yes, 2 again, because angular node is relating to the L value, so L equals 2 angular nodes. Okay, so let's draw a radial probability diagram for a 4D orbital. So basically, this question is asking you, okay, how many radial nodes do I need to draw, essentially? All right, so in order to do that, if we identify the N and the L values given in this orbital, we can just plug it into the equation and determine what kind of graph, how many times does it have to go to 0. So for a 4D orbital, what is N? 4. And then what is L? 2. So if we do the equation, number of radial nodes equals N minus L minus 1. This is going to be 4 minus 2 minus 1. So this graph is going to have 1 radial node. So that means this graph is going to go to 0 how many times? Just once, but don't count the beginning and end. So this graph is going to look like 1. So there's 1 radial node, and then 2. That's it. That's what the graph will look like. So that's a different way to ask a similar question. And so we can get the information from a 4D, from the information 4D, because I give you the N value and the L value. All right. All right, so radial distribution functions, again, is another way we can represent where to find electron density, but this time kind of in polar coordinates, kind of moving outwards away from our nucleus. Okay, so let's do the last one, F orbitals. But I'll be honest, we don't go through F orbitals that often, but let's just go through what we know about our quantum numbers here. F orbitals have 3 angular nodes, right? That is the L value. Those are the different shapes. See how I don't have them labeled because there's just a lot of them and we're not going to go into detail with F orbitals, all right? Okay, so let's look at these questions. How many angular nodes does a 4F orbital have? 3, because angular nodes is our L value, all right? So it doesn't matter if it's 4F, 5F, 6F, all those F orbitals are going to have 3 angular nodes because of the F component, the L value. All right, how many radial nodes does a 4F orbital possess? So a 4F orbital, N equals 4, and L equals 3. So what is the number of radial nodes present? How many? 0, yes. So the graph is just going to look like 1 hump. That's it. 1 hump. Because 0 radial nodes. Okay, then how many radial nodes will a 5F orbital have? 1, yes, because if we do the same stuff again, N equals 5, L equals 3, so the number of radial nodes will be 1. So 5 minus 3 minus 1 is 1. So if we drew the graph for this one, the graph is going to go to 0 once. It's going to look like that. Yeah. Okay. All right. So those are our the meaning behind all of those numbers. The meaning behind them, all right? Because the quantum numbers do have meaning. It's from solving the Schrodinger equation. Okay, all right, so those are our quantum numbers. So now let's actually place electrons in these different orbital shapes. And thankfully, there's not a lot of memorization that has to come here. All the information you need comes from the periodic table. So let's talk about the rules for placing electrons. Right? So if I tell you place, 10 electrons on an orbital diagram, these are the rules that you have to follow. Right? The first rule is Aufbau's principle, meaning, so Aufbau, it is like German, means to fill up. It means you just need to fill electrons in lower energy levels before you start putting them to higher energy levels. So in practice, you just want to fill, 1s orbitals before you start filling up 2s orbitals, for example. All right? So you always put electrons low before you start working up. All right, so that's the first rule. The second rule is Pauli's exclusion principle. That we talked about this earlier when we talked about the spin quantum number. It just means that if you have to place 2 electrons in a box in an orbital, they need to be opposite spins, right? So here's an example. This is okay, but this is not okay. All right, so this is okay, that's not okay. All right, and so the last rule for filling electrons is Hund's rule. And so Hund's rule talks about, the whole idea of predicting where electrons go. We want the electrons to minimize their energy. And so to minimize energy of electrons, what we want to do is maximize the spin in subshells where we have multiple electrons. So here's an example. If we need to put multiple electrons in one subshell, we want to spread those electrons out first before we start doubling up, right? And we want to maximize spin. So for example, if we need to put 2 electrons in a p subshell, we want to spread those electrons out so that they're also the same spin. So this is what we want to draw. We don't want to draw these 2 configurations because these 2 configurations actually have higher energy. So these 2 configurations aren't going to actually happen in real life. So here, we're doubling up before we start filling up the orbital. And in this one, we're not maximizing the spin. So both of these actually violate Hund's rule. Right? So in practice, you just want to spread out your electrons with the same spin before you start doubling up. All right. I'll also point out, let me draw this. If I placed my 2 electrons like this, do I violate Hund's rule? Like this? No. So is that okay? Can I draw it like that? Yes, I can. Yeah. They're just both spin down. I still spread the electrons out. They just happen to be spin down. That's okay. What if I did this? What if I put this electron over, what if I put this electron over here? Is that okay? It actually is still okay. It is still okay. I'm still spreading out those electrons, right? I'm still maximizing the spin. It's just for some reason we like to place electrons left to right because we read left to right. We don't have to place the electrons left to right. All right, so for example, if I had 1 electron like this picture is the same energy as if I drew the orbitals and had 1 electron there. We don't have to put our electrons in left to right. Just for some reason we like to because we read left to right. So just keep that in mind. Okay. All right, so let's write the electron configuration for hydrogen. All right. So here I have your energy level diagram for hydrogen. How many electrons does a hydrogen atom have? 1. Okay, has 1 electron. So we need to place 1 electron on this diagram. Where is it going to go? On the bottom. It's going to go right there. Right, in the bottom. So we follow Aufbau's principle. So we can also write the electron configuration, basically telling the reader exactly where we're going to find electrons. So I want to tell the reader where did I put that electron. So I'm going to say we have that electron in a 1s orbital, and there's 1 electron in there. So I use a superscript 1. Right? So that is the electron configuration for a hydrogen atom, right? Where I can use the diagram here to figure out where is that electron going to go, and then I can write and tell a reader, like, in a word processor, where you will find that electron. Because, drawing these diagrams are hard, but writing where the electrons are in text is a lot easier. All right, so that's for hydrogen. That's placing 1 electrons. Things get a little bit different when we have multi-electron atoms. So for any other atom other than hydrogen. All right, so once we aren't placing electrons on hydrogen, if we're working with any other element, we see that the energy level diagram changes a little bit. But we're still going to follow the same rules, Aufbau's principle, Hund's rule, etc., to place those electrons. So let's use this diagram to write the electron configuration for sodium. So we ask ourselves the same questions. How many electrons does sodium have? 11. All right, so we just place 11 electrons. That's it. Okay, so where are we going to place them first? In the 1s. So we go 1, 2. Okay, that's filled up. Remember, 2 electrons in a box. Where do the next electrons go? 2s. So 1, 2, 3, 4. Then where do they go? 2p. So here's 5. Where am I going to put my 6th electron? Next to it. Right, so that's 6, 7. Then where do I go? Spin down in the same boxes. Yeah, so 7, 8, 9, 10. And then the 11th electron goes where? In the 3s. Yep. Right, and I made it spin up, but I don't have to. I could make that first one spin down. It doesn't matter. All right. Okay, so that's our electron diagram. So we can write the electron configuration, just telling the reader exactly where you're going to put those electrons. So we started electrons in that 1s orbital. We put 2 electrons in there. Then we put them in the 2s orbital. We put 2 electrons in there. Then we put them in the 2p orbital. How many electrons are there? 6. And then 3p, and there's 1 in there. So if you count all those, if you add up all those superscripts, you do see that that adds up to 11. So you can check your work there, right? Okay, and then another way we can write this is using the noble gas configuration, where we recognize that all of these electrons are represented by what element? Neon. So we can write neon in brackets. This is kind of like a save point, all right, where we can just use neon as our save point to represent 10 electrons, and then just write 3p1 at the end. Right, so that neon in brackets takes care of 10 of the electrons for us, all right, and then we just go 1 over to sodium, which is within our 3s orbital. Okay, so we placed electrons in these orbitals. It was easy enough to do because I gave you the diagram. Yeah? Oh, I wrote 3p, sorry. What should it be? 3s, okay, perfect. Yes, 3s, good. Yes, because that's where the electrons are, right there, in a 3s. Okay. All right, so I gave you the diagram. So it was kind of easy to do, to follow Aufbau's principle and and maximize spin, all that. But do you need to memorize this figure? If I asked you, okay, what's the electron configuration of aluminum? No, all of this information comes from the periodic table. All right, I don't actually have to give you this diagram to know that you need to fill, 3s before 3p, then comes 4s. I don't actually have to tell you all of this. All of this comes from the periodic table. All right, so this is why the periodic table is shaped the way it is. We have these, group 1a and 2a. I call this my S block. This is my S block. Right, all the elements over here on the right side of the periodic table, that's your P block. And then all of the transition metals, that is your D block. All right, so if you want to, for example, write the electron configuration of oxygen, just note where oxygen is on the periodic table. I think it's right here. Let's pick a color right there. That's oxygen. So to write the electron configuration, you start at hydrogen and then just work your way up, understanding that this is your S block. Hydrogen starts with 1s. Your P block starts with boron with 2p, because a 1p does not exist. Scandium, that starts your D block, but it starts at 3d. So as you work your way across to the element that you want, just take note of the positions on the periodic table to get where you need to be. So for example, lithium is right here, right? That's where lithium is. So if we start at hydrogen and just work our way there, we see, oh, we need to put 2 electrons in our 1s orbital, 1 electron in our 2s orbital. That's how we get lithium. So to get oxygen, we do 1s, 2 electrons in our 1s, then we completely fill up our 2s as well. And then what's the next subshell that comes after 2s based upon this? 2p, yeah, because boron starts at 2p. And then how many electrons are we going to put in there to get to oxygen? 4, all right? If we want to use the shortcut, kind of back your way up to the nearest noble gas. So in this case for oxygen, it's helium. All right, so helium takes care of 2 electrons, so then we would write 2s2, 2p4 after that, because after helium comes our 2s subshell. All right, Okay, so let's do another one. Potassium, where is that on our periodic table? It is right here, right here. So again, we work our way up to it. So we go 1s2, 2s2, 2p, we completely fill up 2p, so 2p6. Then what comes after 2p, once we're here? 3s, and then how many electrons go in there? 2, and then after 2s, we skip over here. We go to 3p, how many electrons go there? 6, yep, because we want to go all the way here. That's where our target is for s, and we'll just put 1 electron there. All right, so that was me working all the way from hydrogen to get to potassium, but I'd rather just use a shortcut. So what's the nearest noble gas there for potassium if you work your way backwards? Argon, yeah, so we can write argon, and that takes care of 18 electrons for us. So we just actually have to write the next electron, potassium. I know it's going to be an s orbital, but you got to figure out what s orbital it is. So I recognize hydrogen starts 1s, so lithium 2s, sodium 3s, potassium 4s. So this would be argon 4s1. So that's the shorthand way to do it. And honestly, I like the shorthand way better. All right. Okay, let's do zinc. So zinc is, I think, here on the periodic table. So let's do shorthand again. So let's start at argon, because it's the closest noble gas. And then we work our way from argon to the row with potassium, which is 4s. So we're going to fill that up twice for 2 electrons. And then to get from scantium to zinc, what subshell is that? It's a d orbital, but specifically what d orbital? 3d, yes, 3d. All right, so that's 3d. So yes, we went from 4 and kind of dropped down to 3. The energies are similar, so that happens. And then we put 10 electrons there. All right, and then we can do the same thing for germanium. Where's germanium? It's just 2 over. So germanium's right here. And so we can do shorthand again. We can go argon, 4s2, 3d10. But once we go from zinc to gallium, we're in a new subshell. What subshell starts gallium? It's a p orbital, but what p orbital? Which p? 4p. Yes, it is 4p. And I like to just memorize that boron starts at 2p, so that means aluminum is 3p, so that means gallium is 4p. Yes, that's how I get it. Because when you start in the middle, it's kind of tricky. And so I just reference myself to the top of the group. Okay, so 4p, 2 electrons to get to gallium. All right, so that's how we use the periodic table to get electron configurations. All right, so so there are some anomalous electron configurations. Most of these are transition metals, all right? And so what we saw here for like zinc and germanium is that we filled 4s orbitals before d orbitals, and the reason is because these, once we start introducing d orbitals, the energies start to be similar, and so we fill them kind of out of order. And so what happens are there's some anomalous electron configurations where it doesn't really follow our, like the way that I showed you off the periodic table. So some of those anomalous electron configurations are all of the elements in like the group with chromium in it and the group with copper in it. And so this is what the anomalous electron configuration is. If we did the electron configuration for chromium, just like we did before, what we would get is 4s2, 3d4. Right, because chromium is just 4 over. But the thing is that this configuration isn't very stable. And so what we'll actually find is that one of the electrons in the 4s orbital is going to jump ship to the 3d subshell. So what you'll actually find is 1 electron in the s subshell and then 5 electrons in our d subshell. And the reason we do this is because we get a lot of stability back when we have a half-filled subshell. All right, so 5D just gets some enhanced stability, all right, when there's 5 electrons in a d subshell. So we see that's why one of the electrons in our s orbital jump ship. So then now we have 2 half-filled, perfectly half-filled subshells, and there's just a little bit of enhanced stability. So we see that for chromium, and we see that for molybdenum, all right? Okay. So yeah, instead of having 2 and 4, we see 1 and 5 instead. So chromium and molybdenum will do that. We also see something similar for copper. So if we just went through our normal way of doing electron configurations, you would expect copper would be 4s2, 3d9. But you have that d orbital, and it's 90% filled. So what's instead going to happen is one of those s electrons is going to jump ship over to the d subshell to completely fill it. And so what you'll actually find instead for copper is 4s1, 3d10 instead. All right, so it's all of those, the 4th group in our D block and the 9th one in our D block for half-filled and full-filled. All right, so those are our anomalous electron configurations. So copper does it, silver and gold. You'll all see D10, S1 instead of S2, D9. All right, so do just memorize those ones because those ones can be definitely tricky. Okay. So, all right, so we've placed electrons. Okay, so let's look at some other details of our electron configuration. So here are electrons for lithium. Lithium has 3 electrons, so we put 2 in our 1s orbital, 1 in our 2s orbital. So we can talk about unpaired electrons in these electron orbital diagrams. So based upon this picture, how many unpaired electrons does lithium have? Just 1. Yep. So this is 1 unpaired electron because in our 1s subshell, since everything's filled, everything is paired. Right? So lithium just has 1 unpaired electron. Okay, so let's do the same thing. How many unpaired electrons does a nitrogen atom have? All right, so yes, we look at the periodic table. All right, so what might be helpful is if we write the electron configuration for nitrogen. So nitrogen is 1s2, 2s2, 2p, how many? 3, yes, 2p3, right? So if we drew these pictures out, all right, there's 1s, 2s, 2p. So we have electrons in our 1s, electrons in our 2s. Then we fill up our electrons in 2p, but we go 1, 2, 3 to follow Hund's rule. And so we see how many unpaired electrons does a nitrogen atom have? 3, yes, 3 electrons. Okay, perfect. All right, so let's do this a little bit differently. Let's identify all of the neutral elements that contain 2 unpaired electrons in their 4p subshell. Right, so a 4p subshell has how many boxes? 3, yes, p, so 1, 2, 3. All right, so how can we write 2 unpaired electrons? So we can go 1, 2, like that. So basically we need an element that has 2 electrons in its 4p orbital. What element is that? So you look at 4p, it's going to be germanium, right? Germanium has 2 electrons in its 4p orbital. All right. Is there another way we can get 2 unpaired electrons in a 4p orbital? So p4, but also, 2 electrons in a 4p orbital, but how else could we do it? So 1 electron, 2 electrons, so that's 2 unpaired electrons. There's 3 unpaired electrons, but what if we add another electron? It goes there. Now how many unpaired electrons are here? 2 again. So this also has 2 unpaired electrons, but this is 4p, 4 electrons in that 4p subshell. So what element is that? 1, 2, 3, 4. Selenium. Yes, it is selenium. So germanium and selenium both have 2 unpaired electrons in their 4p subshell. Okay, so the idea here is for these last couple questions, did I need to write out the entire electron configuration for germanium or selenium to answer those questions? No, we see that unpaired electrons only ever happen on the outermost electrons because we also always completely fill our inner inner shell electrons. So this gives rise to the idea of valence electrons. So valence electrons are where all chemical reactivity comes from. Oh, that's on the last slide here. All right, so I'll come back to valence electrons. So let's put everything together, all of the rules of quantum numbers together, because I feel like writing, the quantum numbers, the correct quantum numbers for something is rather simple, not simple to do, but easier to do. If I say like, okay, what is, the quantum numbers of the outermost electron on a carbon atom, right? You'll say like n equals 2, it's in a p subshell, etc. So instead, let me show you pictures of diagrams, and you tell me, are they correct or not? And then we'll take it one step further, and if it's not correct, let's identify what what rule is being violated here. All right, so these are all of our different possible diagrams. Is there a diagram that violates Pauli's exclusion principle? Yes. Okay, so remember what Pauli's exclusion principle is related to? It's related to spin. Yeah. So which diagram violates Pauli's exclusion principle? B, yes, because B has an incorrect spin. So how could we make B correct? How could we make it a correct diagram? What quantum number do we have to change on what electron to make it correct? This, which quantum number would we change? MS, yes, that's how we would get it to be correct. All right, which diagram violates Aufbau's principle? So Aufbau means building up, so which one does not build up? C, yeah, so C. How could we make this diagram correct? If I moved this electron over there, and so what quantum number am I changing if I do that? To move that electron from a 2s to a 1s, how do we do that? Which number changes? N, yep, N changes. Okay. All right, which diagram violates Hund's rule? Diagram or diagrams? A, yes, A violates Hund's rule because we don't maximize spin, all right? And so to change this one, I would have to change ML and MS in order to make it right, all right? What about E? Does E violate Hund's rule? Nope, that one's okay. That one's okay. I just happen to write them right to left and spin down. But for some reason, our brains don't like that. But this one is actually completely okay. All right. Okay, so then which diagrams are correct? D and E would be correct, and what elements would these be? D is what? Boron? Boron, and then E has 2 electrons in its p subshell, and so that would be carbon. All right, great. So D and E are correct. Okay, so that's other ways to ask those questions. Okay, so I mentioned in the previous section right here, we don't have to write out the entire electron configuration to answer a lot of these questions. So the outermost electrons are the reason elements behave the way they do. And so we can predict how many electrons are in the outermost shell of an electron on an atom based upon what group number it's in, for the most part. So for S and P block elements, it's fairly straightforward. So the number of valence electrons, like on a nitrogen atom, is going to be 5 because it's in group 5. All right, so those outermost electrons are in the highest N value there. Right? Then some weird stuff happens for D block elements. So for early D block elements, sometimes we include s orbitals, electrons, and then for later D block elements, we don't include, we only include s electrons. So we have a couple minutes, so I think we have time to finish these slides to predict how many electrons are on these different elements based upon where they are on the periodic table. So we can write the entire electron configuration down, but we don't necessarily have to for a lot of these. A lot of it just comes from where they are on the periodic table. So for sodium, the number of valence electrons on a sodium atom, since it's an S block element, there's just going to be one valence electron, right? I mean, you could write the whole electron configuration out, but you don't have to. All right, sulfur is a p block element. So we just look at its group number. So sulfur is in group 6A, so how many valence electrons does it have? 6, yes. Bromine, how many valence electrons on a bromine? 7, because it's in group 7A, right? Oxygen's going to have 6, right? Carbon is going to have how many? 4, because it's in 4A. Silicon's also going to have 4, because it's in 4A. What about magnesium? 2, yeah, because it's in 2A. And neon? Not 0, it's the outermost. So it's actually 8, right? It's actually 8. This is the outermost. Okay, so the ones I skipped over are the transition metal ones, because sometimes they're weird. If they're outer, so early transition metal, so something like titanium, which if you wrote the electron configuration out would be 4s2, 3d2. Titanium actually has 4 valence electrons in it because those 4s and the 3d electrons, they both count. And I know this because titanium can lose 4 electrons. That's why I know titanium has 4 valence electrons. On the other hand, if we look for silver, silver is one of those anomalous electron configurations. It's 5s1, 4d10. So those 10 electrons actually don't count on the in the d subshell. So we see that silver actually only has 1 valence electron, right? Manganese counts as an early transition metal valence electron count. So if we look at manganese, it's 4s2, 3d5. So manganese is actually going to have 7 valence electrons. So the d electrons count in this example. But if we write out zinc, zinc is 4s2, 3d5, or sorry, not 3d5, 3d10. And so zinc, kind of like silver, those d electrons, they don't count at this point, okay, because they're completely filled and they become stabilized. So zinc actually only has, two valence electrons here. All right. All right, I'm sorry I went a minute over, but I needed to get through these slides. All right, so we went over everything for chapter 6. That will prepare you for the midterm next week. So you guys, your midterm is on Wednesday. So my plan is on Tuesday is to do some midterm 2 review. All right? Oh, and remember, I have my review session on Sunday. And we don't have class on Thursday. Yes.